Hi, hello again. Let's carry on. Now we look at the criteria that we refer to in choosing a suitable foundation, right? Okay. Good. Now, to choose the type of foundation, we'll be looking mainly on the loads that is being imposed on by the superstructure of the foundation. Okay, so quickly, if your superstructure or the building is a few story one, then the load reaching it will be quite low, so we could have individual footing or isolated footing, meaning a small building, right? If your building footprint is going to be 50% or more of your building plan area, you may not want individual footing anymore. You may want to combine them and make it into a route that will be easier to cast and more economical. Alright, and if the loads are greater, then you may be looking at putting your rough at a greater depth. Remember the effective depth that we talked about. The deeper you put a foundation in, then the greater the soil barrier capacity will be. Logically, the deeper it is, the soil layer would have sustained the bigger load because of its own self-weight, the friends on top of it pumping it. Yeah, so that will give it a better barrier capacity. Just the issue is, or the challenge is that you got to dig deeper, and a deeper excavation site will need more support, and there's always a risk of the collapse of your excavation site. Right, number 4. With the increased height of your superstructure, then you can consider putting your rough on the ground by increasing the barrier capacity of the soil by doing what? By doing ground improvement. We'll look at these in your chapter 4. We'll pass on the notes. Do look at them, alright, on ground improvement, especially the soil stabilization method. Soil is bad, you can't put any foundation, any buildings on it, fine. Stabilize it, make it stronger, make it stiffer, then you can start using it by putting a reasonable foundation. Alright, now the next set of criteria we want to look at is that when we want to pick a suitable deep foundation. Now, the choice of deep foundation is influenced not only by the load, but also by the condition of the site and soil. Bear this in mind. This is important to remember. Okay. Now, first criteria: the soil near your ground is too soft or too loose. So, a shallow foundation is out of the question. You need to bring the foundation down to greater depth so that the load can be sustained by the ground. Right. Number 2. The loads are so high that there's just not enough pan area to accommodate the size of foundation required. You may have a big enough footing, right? Remember we said individual pad footing are not good enough, not strong enough. We combine them and make it a pad footing. Yes, structurally it could take it, but the soil couldn't take it because the load is just too high. And if you want such a big rough footing, maybe the area is not quite big enough. Remember, not all buildings' footprints are regular, rectangular or circular. Sometimes it's just odd shapes, and coming to the corners and things like that, you may be coming into other people's ground. Remember boundary lines? So it is not feasible. Number 3, this is important to know. The groundwater table. Just have a quick read here. It is higher than the level where the base of foundation is going to be. So higher, that means your foundation is going to be underwater. So when anything constructed underwater is never a good idea, because just talking about the excavation to put in the foundation is going to be a problem. Because why? Because you have to do dewatering. Yeah? We learned this in chapter 2, and dewatering can be expensive, can be risky, and hence it may not be a good option after all. So better just pop in the piles and bring the loads down to greater depths. Right. Number 4, we could have a situation where the nearby buildings are just too close by. They are just congested. It's a building area, so it's difficult to make big excavation, a deep excavation. So in such situation, you may want to consider just bringing one machinery in to drive in the piles. Number 5, you have high superstructures. Usually we have a group of piles under each column, or it's more stable, as you can see, when you put it into greater depth. Remember, we talked about those pylons, transmission lines, uplift forces. Yeah, tall and slender structures always are subjected to winds, earthquakes, all the horizontal forces that can cause moments, right, and overtopping. Number 6, the taller superstructure with many basements, then you could have power rough system. We'll look at this more in detail, very close to KLCC. Why sometimes a high-rise building is alright to put in the rough, but combined with the piles at the bottom of it. And last but not least, structures that are constructed over water bodies, rivers, lakes, coastal areas, and these kind of situation, shallow foundation is just not feasible. Definitely you're going to have legs going down, long legs going down as piles. Alright, and part of the piles are actually coming out as pillars for aesthetic values. When you look up, when you see on the from the water level, lake, see, for instance, you have a structure, a platform, your structure, you can see legs. Those are actually the beginning of your piles, but because they are still above the seabed or the river bed, they are considered pillars, right? But actually they're part of the foundation. Okay, now shallow foundations are known to be more economical than deep foundations. Why? There are certain reasons here. Not always, as you can see, you do not always it's not always feasible to use shallow foundations, but when they can be used, these are the economical factors that you can consider. One, they are constructed using the same method, isn't it? You just form the formwork, say they are square pad footings, you can reuse the same formworks can be reused, and it's the same method. Excavate, put in the reinforcement, and put in the concrete, and that's it. When time is out, take out the formwork, you can move on to the next pad footing, set up the formwork again. So the method is the same. It's repetitive, right? When you have a construction method that is repetitive, materials that are reusable, the formworks, then become cheaper, right? And it becomes faster. Number two, they are carried out by doing open excavation to small depth, just a small depth. So presumably small depth, then it's safe, it's quick, it is not tedious, it is not something that's complicated. And finally, sometimes deep foundations, depends on what kind of deep foundations, it could be complicated. You need special machinery. For example, bored pile. Bored pile is not so simple as just bringing the pile, pop it in, and that's it. No, you have to drill a hole. You may have under reaming to make a bigger base, yeah, for uplift. Then you take out all the soil with all the spoils out. You have to find somewhere to throw them away. You can't just throw it to your neighbor's ground. Then you put in the reinforcement, adjust them and line them properly. Then put in a driving pipe to put in the concrete, compact the concrete, and make sure that everything is aligned. So it's quite a bit of work there, and it could be quite expensive and time consuming. Alright? Take a look at this diagram to show us the relevance of the height of a building, right, to the type of foundation that we should be adopting on site. Now, small building, few story heights, perhaps isolated footing is good. Every single column coming down, you have a small pad taking it. If you have a higher building, then the pads will be closer because the columns are closer. You may want to consider 2 columns or 3 columns coming down, combined into one pad footing. And if the footings are so many, they are covering more than 50% of your footprint of the building, you might as well just put them all together and make it into slab or a raft. Alright, if the building is going higher, now you still want to use a raft, it's fine, because perhaps the soils at your shallow depth is still alright to bear the load. Now bring it down to a greater depth, and the extra depths that you want there, you have there, can be used as basement, car parks, or just underground offices and things like that. Okay, and just look at this diagram here, E. We talk about wanting to build a high-rise building, but our ground is bad, but we still don't want to use deep foundations for all sorts of reasons. Maybe it's difficult to mobilize the rig in, things like that. So you may want to stabilize the grounds, and then once it's stabilized, strength is improved, stiffness is improved, you could probably put in a shallow foundation. Now in this case, they pop in a raft eventually, right, onto the improved grounds. Or normally we have piles going down, deep down, pile groups in fact, for high-rise building. Or we have multiple basements, so here it's a pile raft system. So these are all basements. You have a raft here before you start putting the piles, right? So this is a combined system. Okay. Now, what are the design criteria that we look at in designing the foundation? First and foremost, we look at the bearing capacity failure part, and the safety factor we're looking at is 2.5 to 3.5. As you can see, they are quite high, 2.5 times to 3.5 times, sometimes even as high as 5, depending on how confident we are on the bearing capacity that we can derive from the ground. Alright, and higher safety factors are usually adopted when your soil is fine grain. Fine grain means clay. So everybody knows when it's clay that you find on site, you do not quite like it. It can be quite dangerous, soft like plasticine or worse. The site has got not very comprehensive investigation done, so SI is not completed. For whatever reason, you can't get hold of it or things like that. So you may, because you are not sure of the foundation, the foundation soil, you may want to up the safety factor. The variability of the soil is high. One part to another, you have all the boreholes in, and you still get all the variation. You are not sure now wherever you pop in your foundation, whether it's going to be safe or not. And the structure is of high importance, and you cannot allow any slight failure. So like KLCC, you cannot allow it to start tilting and things like that. So these kind of structural safety factors will be very high for the foundation design, and the possibility of design loads actually occurring higher than what you expect. So another situation, alright, that you have high safety factors. What about settlement? So in terms of settlement, we are more concerned about differential settlement actually. And when we talk about differential settlement, means one side is settling more than the other. We sometimes call it angular distortion. And here are some reference charts that you can have. Angular distortion, in this case, whatever you're seeing here is actually the settlement over the column spacing. Alright, these are the numbers you get here. Now, looking at shallow foundations in terms of design, the settlement that we usually permit is like 25 to 50 mm, so it's no more than 5 cm. It's not a lot there, right? For the total settlement. And see that if you are using a raft, then the settlement that is allowed is bigger. Why? Because for a bigger surface, you can have a stabilization effect compared to individual pad footing, right? Okay. Now, we are going to have a small discussion about why basements are nice to have, right? So as you can see here, it's a high-rise building, and in order to put your pad footing down here, see, this is your pad footing, and you can see some parts are thicker, yeah, these are thicker, and they are thicker where? Near your columns coming down. It makes sense, right? Where the loads are coming down from the columns, you want it to be taking the more load than the parts that are not having the column coming down. Hence, the parts that are near the columns or under the column are usually thickened. Alright, that is common for a rough foundation design. And in this situation, you will need to excavate first to the desired depth. That will be your DF, right? Where you want to place your the rough foundation, and then you start to put in your reinforcements and so on and so forth, so you can put the building up. So the soil is actually not being put back. Alright, that's how you can have a basement there. And just look at this note here. You have waterproofing membrane to make sure that water doesn't go through your concrete into your basement building. That is very, very important. Alright, and our own KLCC, you may have already known, you have visited the place and look at the documentary on it being shown in there. It's a high-rise building, 88 stories high. And what we have here is that we put it on a large raft. However, under the raft, we have still piles going in, because the grounds around here are not especially good. You have this candy hill formation and a limestone down there, and the limestone can be heavily weathered, and they are not reliable to sustain the big loads. Hence, they have this raft to put it to bring the foundation down to take advantage of the greater depths and greater bearing capacity of the grounds. Alright. So, and the raft foundation that is under KLCC is actually 4.5 meters thick. Can you imagine that? That is as high as a story now. Okay, and the loads that are taking for each tower is 1.14 megapascal. You can start calculating how big that load is. Okay. And for design of deep foundations, you can see here, we are always looking at in-bearing and the skin friction. Okay, whether you are sitting into a hard layer, or you can drill it, pre-drill and socket it in, or they are just simply floating in the ground, having this friction to resist it. Okay. And the selection of piles also can be looking at the dimensions of it, the type of materials, the shape of it, and whether they are going to be driven, that is like to be hammered in or to be vibrated in, or they are cast in place where you drill a hole, put in the reinforcement, then cast the concrete in. And these are again the dimensions that we are looking at. So these are just for quick references. Alright. If we are looking at the actual capacity analysis, the safety factor is about 1.5 to 2.5, and this diagram here you can see, if you are constructing the place where you have existing tunnels, buildings and all, you want to consider the vibration that's coming in from the way that you are putting in your piles, whether it's by hammer, vibration, or any drillings that's going on. Okay, power load test, we have seen this before. Once you have put the load in with the design loads and all, you want to make sure that it is as you need it. It's going to take the loads that you have designed it for. Okay. Settlement, you can look at some of the equations that I pop in for you in the modules, alright, similar to those we have learned in chapter 2. Okay, we'll just pause it for a bit for the last part of power group.